Okay, good morning everyone. Let's get started with lecture 9. As you may hear, my voice is a little bit gone. I got something over the weekend, but I hope that me coughing is not too loud. I'll try to mute the microphone before I go into a coughing fit. So I hope everyone had a good weekend. So far we've been looking at elastic collisions where no energy is lost during the collisions. But as you can imagine, in reality it's a little bit more complicated, and there are inelastic processes in the collisions, and you saw one of them. In the small Newton cradle, the efficiency was something like 98%, at least that's what they claimed. But the big Newton cradle, when they had those wrecking balls crushing into each other, they got one or two nice transfers, and the rest all went into some kind of deformation. And of course, it was quite loud. So we're going to deal with inelastic collisions today. We'll do things in the lab frame, we'll do things in the center of mass frame as before, but we're going to see what happens there with the inelastic part. So this is kind of the simplest case you can imagine. You've got one body coming in, the other one is at rest, then something happens during the collision, and then afterwards both bodies have some kind of velocity. And during the collision, this loss in energy is, well, sound, deformation, heat, and so on, or a combination of those. So let's start just with the usual equations there. We've got the conservation of momentum. Conservation of momentum. M1 U1 equals M1 V1 plus M2 V2. So U2 is not, so that's, and will also stay in one dimension, so that just makes things a little bit easier. So this is the first one, and the second one is the energy conservation. We have before the usual 1/2 m1 u1 squared equals kinetic energy of the two bodies afterwards, 1/2 m1 v1 squared plus 1/2 m2 v2 squared. But now we have this delta E. So let's just make this our equation 1, and this our equation 2. We're going to need them a little bit. So as you can imagine, algebraically, it's not as easy as it used to be. So what I'm going to do first, I'm going to square the first equation which we have up there. So I get m1 squared u1 squared equals m1 squared v1 squared plus m2 squared v2 squared plus the cross term 2 m1 m2 v1 v2. So that's the first one. The second term is 2 m1, the second equation. So if I take 2 m1 of this this equation, I'll end up with m1 squared u1 squared equals m1 squared v1 squared plus m1 m2 v2 squared. And then we have, I'll just write it here at the end, so we've got plus this 2m1 to m1 delta E. I've written them this way because now you can see that if I subtract those terms, I get a few things that cancel and a few things that are left. So if I now take this one and take a minus of those, I end up with this minus this is naught equals this minus this is naught. I can take out the M1, M2 and the V1 squared, V2 squared. I get plus M2, M2 minus M1, V2 squared, and I'm left with the M1 delta E at the end. Now we still have to solve, sorry, I forgot one term, this one, plus 2m1 m2 v1 v2 minus, so that basically goes down there. We've got now an equation where we've got v1 and v2. We need to get rid of one of those. Let's use m1 v1 equals m1 u1 minus m2 v2. So this is from the first equation. I've just rewritten it as m1 v1. And if I plug that into here, this m1 v1 in here, I get, so I'm just going to write m2 minus m1 v2 squared plus 2 m1 v1 m2 v2 minus 2 m1 delta E equals naught. I've basically just repeated that line. I'm gonna put this in here, and I'll end up with m2 minus m1 v2 squared plus 2 m1 u1 m2 v2 minus 2 m2 v2 squared minus 2 m1 delta E equals naught. Gonna simplify that, and I'm gonna end up with a quadratic in V2, M2 plus M1 V2 squared. So that sign changes because of this term. When you put that over, you get here plus sign minus 2 M1 M2 U1 V2 plus 2 M1 delta E equals naught. Now we have a quadratic in V squared, and I hope everyone remembers this formula: ax squared plus bx plus c equals naught. I hope everyone does it. The solution for that quadratic, if I'm not mistaken, is not in your formula book. So you have to know that this is x, the solution is minus b plus minus the square root of b squared minus 4ac over 2a. And that's how you arrive at those terms down here, equation 3 and equation 4. Taking consistent solutions with elastic case, so when you take delta E equals 0, you should arrive at what you should get in the elastic case, and that defines whether it's plus and minus sign. So in physics, you often come across quadratic terms which you need to solve. and one of them makes more sense than the other, so you have to be careful what you're using there to choose the right sign. Now, if you look at this in the lab frame from the, I'll go quickly back. So you can imagine that, well, you get a limiting case. You have here delta E, which is, so this is positive, 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 positive. You have a minus sign. So at some point, if delta E is large, this is going to go to 0. And this is kind of the limiting case. This is what's written underneath the square root. Has to be larger or equals than 0. And if you rewrite that, you get this term, delta E smaller than this one. So I'm sure to some of you, this term looks familiar. So if we have delta E smaller equal M1 M2 over 2 M1 plus M2 U1 squared. I'm quickly going to rewrite that so it becomes a little bit more apparent. M1 M2 over M1 plus M2 U1 squared. And this is 1/2 mu U1 squared, because this is the reduced mass of the system. And this is also actually quite a useful property which we're going to use for the rest of the lecture. Now, as it says, this is the maximum when the two bodies are sticking together in a single object after collision, and you have V1 equals V2, and from the momentum conservation you end up with this term, so V2 and V1 equals this term in 1 dimensions. So this is sorry, this is in the 1D case. Now, there's something I've already briefly mentioned in lecture 7, the coefficient of restitution. Some of you may have had it already during A levels, but for everyone else here, the coefficient of restitution is given as the absolute of the relative or the speed relative separation, so after the collision, over the difference before the collision of approach. Now, working it out, here you start with the difference, V2 minus V1. This is from the slide, from 2 slides before, so those equations 3 and 4. You take the difference, and well, when I did my math degree, the professor usually said, as can easily be shown. If he said something like that, it meant it could be shown in a few lines. If he said, as one can prove, it probably was several pages from step A to step B. I'm quickly going to show you the key steps there, what to do, but I'm sure you can figure it out yourself. So you basically take the top term times M1 over M1. You want to get them on the same fraction, so you basically have to multiply the top one with M1 over M1 and the bottom one over M2 over M2, and then it simplifies, as it says. You can, well, maybe just quick note there. So V2 minus V1 equals, you have this 2M1 M2 U1 plus this horrendous root over 2M2 M1 plus M2, and then minus 2M1 squared U1 squared, U1 minus that root over 2M1 M1 plus M2 So here, this term you multiply with m1 over m1, and this term you multiply with m2 over m2. Then the part down here is equivalent. You can put it up on the same line, and a couple of terms cancel, and you arrive in the end at something like u1 square root of 1 minus 2m1 plus m2 over delta E m1 m2 u1 squared. And if you then divide that by u1, you get to the coefficient of restitution. So that's basically what we've done, is factorizing it, then simplifying, and then dividing by u1. That was the last step. And then we arrive at this term. If we take out u1, we have here now the coefficient of restitution. And we have here this T prime is the reduced mass in the velocity of approach, and we'll see later that this is the initial energy in the center of mass frame. So the two limiting cases sorry. Again. This is the limiting case. E equals 1 is completely elastic, so you see no energy is lost, and E0 is perfectly inelastic. And in general, as we've had it in the Newton's cradle before, there's some energy lost. Now, there's one special case which I quickly like to go through. If we hit a stationary target, so if V1, if V2 equals U2 equals naught, then the coefficient of restitution E equals V1 over U1. So that's pretty simple. This is velocity after over velocity before. We can rewrite that at, it's often, of course, quite difficult to measure the velocity before and after. But if you take, say, this ball and let it bounce, there are a few things you can measure. You can measure the height before and after the collision. And since we can rewrite that as height after, height before, because all potential energy the ball had up here is converted into kinetic energy and then going up again. And well, everyone who's playing sports, table tennis, tennis, you would like to have the ball bounce much better than this one. But there, all the kinetic energy has been directly converted here. You can see it in deformation, and that's why the ball is not jumping. And this is how in sports you qualify also whether the balls you're playing with are fit for purpose. If you play table tennis and the ball is gone soft, then it's not fun. Now, we've worked with the lab frame. Let's have a quick look at the center of mass frame and see whether we can get the equivalent equations. Now here we look at the perfectly inelastic collisions. We have two bodies, U1, M1, U2, M2 arriving. We do the transformation into the center of mass frame, which you all know how to do. The velocities are transformed and shifted with the velocity of the center of mass frame. and after the collision is at the combined body is at rest in the center of mass frame. And this is really, really useful and important to remember that in the center of mass frame the overall momentum is zero. The only way the overall momentum of a single body can be zero is if that single body is at rest. So at end of lecture 6 we showed that T lab equals kinetic energy in the center of mass frame plus 1/2 the kinetic energy of a body with mass m. This is the sum of all masses times the velocity of the center of mass frame squared. So if you then rewrite that, TCM equals T lab minus 1/2 m1 plus m2 VCm squared. I've just plugged that in. We're dealing with two masses, m1 and m2. So this is the kinetic energy in the center of mass frame. Now, if we lose some energy in the center of mass frame, we're going to lose the same amount of energy in the lab frame. So delta TCM is the same in the lab frame. Now, the maximum kinetic energy which I can lose is TCM, because afterwards there's no kinetic energy in the center of mass frame. So the max energy that can be lost is TCM is 1/2 m1 u1 squared plus 1/2 m2 u2 squared. This is our T lab minus 1/2 m1 plus m2 VCm squared. So this is then the overall mass times the velocity of the center of mass frame in the lab frame. So we're quickly going to revisit this relationship. TCM equals kinetic energy in the lab frame minus this, what I've just written down there. In lecture 6, we had this similar example of two bodies, M1 at x1, center of mass, but there they were coupled with a spring. Here they are not coupled with a spring. So we're going to construct that and going to derive what's written there in the red part. So going to make use of xcm equals sum mi xi over m, sum mi. So that's a standard derivation. X equals x2 minus x1. And x1 prime equals x1 minus xcm. Becomes then minus m2 over m1 plus m2. X is equals minus m2 over big M x. Now, TCM, kinetic energy in the center of mass frame, is 1/2 m1 u1 squared plus half, sorry, forgot the prime there, 1/2 m2 u2 prime square. I've already written out x1 prime. So I'm just going to rewrite that quickly. So x1 prime equals minus m2 over mx, and x2 prime equals m1 over mx. From that, if we take the time differentiation, we end up with u1 prime equals minus m2 over mx dot, and u2 prime equals m1 over mx dot. And with this, we can rewrite the kinetic energy. We use that to get TCM. TCM equals 1/2 m1 times minus m2 over m squared plus m2 m1 over m squared. I'll use these brackets. X dot squared equals 1/2 m1 m2 over m squared m2 plus m1 x dot squared. And if we then, this one is of course also m, that cancels this term, and we end up with 1/2 m1 m2 over m x dot squared, and this is of course the reduced energy there. So this is what we end up with. It was shown the reduced energy, and if we rewrite that now going back to x dot, what it was before from the definition of x, we can see we can rewrite that as u1 prime minus u2 prime squared, and also as u1 minus u2, because the shift is with respect to VCM, and if we subtract both terms that have been shifted by the same amount, of course the difference remains the same. So these expressions give the center of mass kinetic energy in terms of the relative velocities in the center of mass and lab frame with reduced mass mu. So we can take the relative velocities, and that is sufficient, and that is quite a useful property which we can and will use throughout the lecture. Now, let's revisit the coefficient of restitution in the center of mass frame and make use of what we've just shown, how sorry. So let's see whether if we work with the center of mass frame, things actually get easier. Everything is written on here on the slide. I'm quickly going to guide you through. So kinetic energy in the center of mass frame before the collision, well, you can write it down like that. Final kinetic energy in the center of mass frame is this, and conservation of energy demands that the initial is the final kinetic energy plus whatever energy has been lost. Now, if you plug this in, what you've written up there, into this formula, you end up with this. This is T initial, this is T final plus delta E. Now, if you divide this term now with divided by the T initial, so if you just divide that by T initial, you end up with this term. T initial becomes this over itself is 1. You move that over, and you're left with this term, V1 prime minus V2 prime squared divided over U1 prime minus U2 prime squared. You take the square root. Sorry, you have to be careful here with the signs. You need ideally the absolute signs, and then you also can fix the square root sign to the positive. And we arrive at the same expression as before, but now T prime is T initial in the center of mass frame. So if you rewrite that coefficient of restitution now as the relative velocities after divided by 4 in the center of mass, since they are shifted by the same amount, it's also in the same in the lab, and you get the coefficient of restitution in this term. The key message to take away there is that only in the center of mass frame can all the kinetic energy be converted into something else. For E equals naught, the two particles coalesce and are at rest in center of mass frame. But if you look at the lab frame, they might be still moving. So in the lab frame, they might still, this one body still might have kinetic energy. So for the remaining minutes in this class, I would like to go over this example. So we have an example of an inelastic process that has something slightly reversed. So a calcium nucleus, mass m, travels with velocity u naught much smaller than c. I think by now everyone hopefully sees that as a particular thing to pay attention to. This means we can deal with it non-relativistic. You might come across some examples later during your course where this is not the case anymore. Here it's the easiest one. We can deal with it non-relativistically. In the lab, it decays into a sulfur nucleus, mass 4/5 m, and an alpha particle, mass 1/5 m. Energy delta T is released as kinetic energy in the calcium rest frame, and a counter in the lab detects the sulfur nucleus at 90 degrees to the line of travel. What is the speed and the angle of the alpha particle in the lab? So this one, as I said, is important, and let's quickly set the problem up. Let's go over here. So what do we know? Well, we're given m, we're given a delta t, we're given u naught, and we're given an angle of 90 degrees. So these are the things we can take away from the question. Now, lab before, we've got the particle with m moving at u naught, and lab after, we have here, just going to continue the line, we've got one particle going out here 90 degrees. That's our sulfur particle with V1. So that's our sulfur at 4/5 m. Kind of explosion or whatever you would like to visualize that. And we've got theta 2, we've got the alpha particle going at a velocity v2. So this is what we in the lab observe. Now if we go in the center of mass frame before, well, u prime equals naught because, well, there's just one body in the center of mass frame. Overall momentum is naught. So the only way it can be is that the velocity in the center of mass frame is naught. And that also means we know immediately the velocity with which we can transform between the center of mass frame. So VCM equals U naught to make this frame stationary with respect to the particle. Cm after. So just draw a little coordinate system. We've got here the x, the reaction, and we have here the alpha particle. We have the sulfur going up here with V1 prime and V2 prime. They have to be in opposite direction. Again, overall momentum is naught, but they're now whizzing off in different direction. That's 4/5 m, and that was 1/5 m. So this inelastic decay can be caused by the internal potential energy given in the nucleus. It is unstable, and suddenly the internal energy is given out in kinetic energy. Before, we had two particles coming together and then moving on as one. You can imagine that as the other way round. One particle coming up, something's happening, and they whiz off in different directions. Now here we have to work in a combination of the lab frame and the center of mass frame to get θ2. So what do we want? Wanted is θ2 and V2. Now, as before, we look at the vector diagram. It's drawn here on the right-hand side, and I'm not gonna draw it again because I think it won't turn out as clear as the one up there. So the energy delta T is released as kinetic energy in the center of mass frame, and we know that this velocity of the center of mass frame is U naught. So if we start constructing it in the center of mass frame, or in the center of mass frame, we get V1 and we get V2. If we transfer it back into the lab frame, we have to boost V1 prime to get V1, and we have to boost V2 prime by VCM to get V2. What we know is we have a right angle here, and that's really key to take that away from the question. Really try to sift through the question and see what you can get. And what we want is θ2 and the velocities. Now, so what and how do we start there? We know that the momentum in center of mass frame we know before the collision it's naught, after the collision it's naught, in the center of mass frame the momentum is always naught. So 4/5 m1 v1 prime equals, let's just do that, minus 1/5 m2 v2 prime equals naught. Sorry, I've already used the, so that's m1 and that's m2. And with that we get a relationship between the velocities v2 prime equals 4 times v1 prime. That's probably not a surprise. Yep. Yep, that should be 2, and the primes that. Thanks for pointing that out. So momentum of the particle of the sulfur, momentum of the alpha particle, and they have to be naught. Now, whoops. The energy, let's just do the energy as well. Delta T equals, before we have nothing and everything is being converted, so it's basically the opposite of an inelastic collision. So all of the energy is being converted, is 1/2 4/5 m v1 prime squared. So that's the sulfur plus 1/2 1/5 m v2 prime squared. And that, if you use the relationships from above, you can rewrite that as 1/2 4/5 m v1 prime squared plus 1/2 1/5 m, and you just plug in the relationship from above. 16 v1 prime squared equals 2 m v1 prime squared. Now, if we now know we are given delta t, so we can rewrite the velocities v1 prime equals delta t over 2m squared, and I can do the same with v2 prime equals 8 delta t over m and the square root. So this delta t is part of the equation which we've been given. Now, the next step, we've been dealing with the lab and with the center of mass frame. The next step is, of course, we need to go transform to lab frame. And that's where this diagram comes in. So we have to boost the v primes by VCM equals U naught. I'm not going to solve the problem completely, but I'm going to outline the main steps and what to take care of, and the rest is pretty straightforward. So cos beta equals U naught over V1 prime equals 2m U naught squared over delta t and the square root of that. This is what you can make use of, this right angle you have here, and you also have it up here, and with that you can immediately work out that the cos is this part adjacent to the hypotenuse, and with that you can solve that. The rest is you use the cosine rule and the sine rule. I hope that by now that everyone understands, if you go back between lab frame and center of mass frame back and forth, then your trigonometry basics need to be firm. If you use the cosine rule, we use the v squared, v2 squared equals v2 squared prime plus u naught squared. I'm in the lower triangle now, dealing with with V2 here, so I'm gonna just go up. Cosine of this is this minus the sum of both, the product minus 2 V2 prime U naught cos 180 degrees minus beta, and that of course 180 degrees minus beta gives plus 2 V2 prime U naught cos beta. So here we have everything in terms of U naught and delta t. We can rewrite that and solve for beta, because we know this one, we know this one, and we can solve for beta as a result. And for the other one, we're going to use the sine rule. So where we're going to look at sine theta 2, which is also down here. Sine theta 2 versus this is sine theta, sine of this angle over that. So sine, sorry. Sine theta 2 over the opposite V2 prime equals sine 180 degrees minus beta over V2. And if you know your trick, so these are the steps again. Now theta 2 is, we have worked out beta before. We know the rest with respect to U naught and delta t, and with that we can solve this problem and work it out. So these are a couple of examples of inelastic collisions, and that is also the last inelastic collision. Next lecture we're going to do with resisted motions, and that will be tomorrow morning at 9 a.m. And I hope by then my voice is also a little bit more reliable. So thanks and have a good day.